Hello students, welcome to the next part of our chapter. Now we are discussing dual nature of radiation, or what we call de Broglie waves. Now some phenomena of the light like interference, diffraction and polarization, we can easily explain them with the help of wave theory of the light. But then there are some experimental effects like photoelectric effect is there, Compton effect is there. These effects can be explained only using the Planck's quantum theory of light, which consider light in the form of particle. So there are some aspects which can be explained by considering light as a wave. There are some other parts which can be explained using the particle nature of the light. So this shows that the radiation or the light is possessing a dual nature. This means sometime it behaves as a wave, sometime it behaves as a particle. So de Broglie, keeping this thing in mind, that if light can show both the characters, sometime as a wave and sometime as a particle, then he thought that the material particle should also possess the dual character. That is, the material particle should also display wave-like characters, wave-like properties. So if light waves can show wave character as well as particle character, then the material particle should also show, along with the particle behavior, the wave-like behavior. So from here he originated the idea of the dual nature and gave the concept of the de Broglie waves. We want to derive the de Broglie equation. According to according to the Planck's quantum theory of the light, the energy associated with the quanta of photon is given by E is equal to h nu. Nu is the frequency of light. From Einstein's mass energy relationship, we have E is equal to mc square. If we compare equation 1 and 2, we have h nu equal to mc square, or we can write this as hc over lambda equal to mc square, because we know that we can write nu as c by lambda. One c get cancelled from here, lambda is equal to h over mc, which we can write as h over p, where p is equal to mc, which is nothing but the momentum of the photon. So this equation is valid for the photon, which is traveling with the speed of light, which is not a material particle. Now, if de Broglie's hypothesis is correct, if dual nature is also applicable to the material particles, they should also show the wave-like character, then they should also possess the wavelength. So by keeping this thing in mind, if this equation is applied for a material particle, so if for a material particle we have mass m which is moving with velocity v, then for this material particle the same equation can be written as lambda equal to h over p equal to h over mv. This equation which we have just written, this equation is known as de Broglie's wave equation. From this equation 1, we can consider an important thing for the light, the radiation, that wavelength is a characteristic feature which belongs to only to the waves. Momentum is a characteristic feature which only belongs to the particles. So from equation number 1 applied to the photon, we can see that both characteristics for the light as well as particle are present in one factor, one equation, which indicates the correspondence or the dual property of the radiation. It behaves as a wave as well as the particle. Similarly, in the second equation, we have wavelength, which is a characteristic feature of the waves, momentum, which is a characteristic feature of the particles. So this de Broglie wave, it actually describes a wave associated with every moving material particle, which is called as the matter wave. Now if we discuss the equation number 2, in this equation if we put velocity of the moving particle equal to 0, then the wavelength becomes equal to infinity. This means that this wave can be possessed only by a particle which is in motion. Only then its wavelength will be finite, which we can easily determine. Moreover, there is no presence of charge of the particle in this equation. That's why these waves are known as matter waves. Matter waves means these are possessed by the particle which possess mass. Third point, they are not electromagnetic in nature. Matter waves are not electromagnetic in nature because electromagnetic waves are associated with the charged particle, accelerated charged particle, and because in equation number 2 we do not have any charge associated with the particle, this means that these waves are not electromagnetic but only materialistic in nature. And fourth point, we also confirm from the equation number 2 that wavelength is inversely proportional to the momentum or the velocity of the charged particle. So greater the velocity of the charged particle, lesser will be the wavelength, or smaller is the velocity of the charged particle, greater will be the wavelength of the charged particle. Now, macroscopic objects in our day-to-day life do not show wave-like properties. Reason: this wavelength is also inversely proportional to the mass of the material particles. The mass of the material particle in our day-to-day life is very, very large. That's why they possess wavelength which is too much small to be observed. But if we are talking about the atomic particles, subatomic particles, electron, protons or neutrons, then because they possess very small magnitude of the mass, their de Broglie waves can easily be detected. Last, we are trying to find out the de Broglie wave of an electron. Suppose we have an electron which is accelerated under a potential difference V. So when electron is accelerated under potential difference V, work done on the electron will be W equal to EV. So electron will gain this much energy, and this energy will appear in the form of kinetic energy of electron. That kinetic energy will be K equal to half mv square, which we can also write as P square by 2m. So if we compare both the equations, we have K equal to P square by 2m, or we can write P as momentum of the electron as P equal to under root 2mk, or it will be equal to 2m ev under the root, because it is also equal to ev, work done on the electron. So if we use this value of momentum in de Broglie equation, which is lambda is equal to h by p, we will get the de Broglie wavelength for electron, lambda equal to h over under root 2 mk, or h over 2me into v under the root. So this is the de Broglie wavelength of the electron. We know that for the wavelength for the electron, mass is 9.11 into 10 to the power minus 31 kg, charge is 1.6 into 10 to the power minus 19 joule, value of Planck's constant is 6.63 into 10 raised to the power minus 34 joule second. So if we substitute all these values in the de Broglie wave equation for the electron wavelength, we have 6.63 into 10 to the power minus 34 divided by 2 into 9.11 into 10 to the power minus 31 into 1.6 into 10 to the power minus 34 into V whole under the root. After solving, we get 12.3 into 10 raised to the power minus 10 divided by square root of V, which gives us final value 12.3 angstrom over under root of V. So this is the expression for the de Broglie wavelength of an electron in the unit of angstrom. But we are to use the unit nanometer for the wavelength, not the angstrom. So this wavelength can be expressed as 1.23 into 10 to the power minus 9 over square root of V, which is equal to 1.23 nanometer over square root of V. So just by substituting various values of the accelerating voltage, we can find out the value of the de Broglie wavelength associated with the electron. Davidson and Germer performed an experiment which proved the existence of the matter waves associated with the electrons. If we put the value of the accelerating voltage equal to 120 volt, then the de Broglie wavelength comes out to be 0.112 nanometer. Now this value of the wavelength associated with the electrons is having the same order, which is also the spacing between the atoms inside a crystal. This means that these matter waves associated with the electrons, they can be used in the electron diffraction experiments in order to study the crystal structure. So matter waves are actually associated with the material particles, but they can be detected and find only for the subatomic particles or the microscopic particles. Thank you.